Okay, today we are doing our test review video and over Unit 2, Atomic Structure. We didn't go too much into atomic structure as far as the physical structure of an atom, only because I would like to go over that in more detail when we do quantum numbers and electron configurations and we learn about the electron clouds and orbitals. So, but we did go into like what each of these boxes represent on the periodic table, and we went over the history of the atom, and we went over the some vocabulary like isotopes and ions, and we learned what ions were. So that's basically what the test is going to be about, not necessarily the actual structure of an atom, but more of the history and some basics that you'll need to know when we go into orbitals and actual physical structures of the atoms. So I would suggest looking at your quiz. You should have that back by Monday. Look at your homeworks. I'm actually going to put the answers of the homework at the back of this video so that you can check your answers. And I would suggest looking through your notes, all of them that we've gone through, your bell ringers. The test, what it's going to be like, it's going to be like your last test. There will be a section of matching questions. So a whole list of questions with a word bank, and you're going to choose from the words. There are going to be extra words. There's going to be words that aren't used. And then there's going to be words that might be used more than once, just like the last test. Then there's going to be a section of multiple choice. There'll be a section of short answer and some calculations. So please make sure you bring your calculator. I will not allow you to use your friends' calculators for obvious reasons, and you cannot leave the classroom once class starts to go disrupt another class to use their calculators. So please be responsible, bring your calculators to the test on test day. We're going to get started. So the first section is just like vocabulary. So let me push this. Okay, so the first question is, who discovered that the center of the atom was very small and dense with an overall positive charge in his gold foil experiment? So remember, guys, this is Rutherford. I remember you had some really good questions about this experiment. Questions I didn't even know the answer to, and we researched them and found them out, and that was really cool that you guys were thinking about the topic and wanting to know more, so good job on that. The next question, the subatomic particle with a positive charge is called the proton. Next, the blank is always equal to the number of protons. The number of neutrons plus the number of neutrons that the atom has. So that's going to be our mass number. So the mass number is just protons plus neutrons. Sorry, I thought that was like supposed to be a superscript. Okay, an atom that gains an electron will have a blank charge. So if you're gaining an electron, remember electrons have a negative charge. So if you're gaining something negative, you're going to have a negative charge. Okay, so E, according to Dalton, atoms of different elements will be different. They're going to be different. Okay, the blank of an atom is the weighted average of the masses of the different isotopes of that element. So remember, guys, the atomic mass you're looking at on the periodic table, okay, like this. So this isn't like exactly what iron weighs. It's a weighted average of all of iron's isotopes. So remember, that's not exactly how much it weighs. It's a weighted average. And that goes for all of these guys on the periodic table as well. So that's going to be called atomic mass. Okay. G, both the neutrons and the protons are found in the nucleus. Okay, so we all know in the nucleus protons, neutrons are found. I believe you guys should have learned that in 7th grade, but just in case, we're bringing you all up to speed so you can't say I didn't tell you. Okay, I'm going to move the paper down. Okay. All right, so the atomic number of an atom is always equal to the number of blank. So if it's the atomic number, remember the atomic number is that, this number right here, okay? So the atomic number, it equals the number of protons for whatever element. So for example, titanium has 22 protons, okay? Scandium has 21, okay? So the answer for H will be protons. All right, I, the proton has a mass of approximately blank, okay? We're just going to say approximately 1 AMU. If you go to IB chemistry or college or whatever, you're going to learn that that's not exactly true, but that's why I put approximately. So for your 10th grade class, it's going to be 1 AMU. Next, Thomas discovered the blank in his cathode ray experiment. So remember, this is the experiment where he had the gas in the cathode ray tube, and then that gas was attracted to the positive side. So he said, well, since it's attracted to the positive side, it must be something in there that is negative. So he discovered the electron. Okay, blank are atoms that have the same atomic number but different mass numbers. So remember what we said, it has the same atomic number. So that means, for example, boron, move this up, boron's atomic number is 5. So we know there's 5 protons in boron. So if it says atoms that have the same atomic number but different mass numbers. So remember, when we take mass into consideration for this year, we're going to assume that the mass is only composed of the protons and neutrons. But remember, we have talked about the fact that they're not all exactly 1 AMU, and that the electron actually does have mass, but only when it's measured, and it's a weird thing. So in 10th grade, we only take into consideration mass numbers to be protons plus neutrons. Remember, this represents the protons. So then it's an atom that has the same protons but different neutrons. So do you remember what has the same protons but different neutrons? That's going to be called an isotope. Last year, I noticed that kids have a confusion about the difference between ions and isotopes. Not all of them, but last year I did notice the kids getting a little confused. Remember, this is a change, this is an atom with a charge, so it's a change in electrons, okay? And remember, isotopes is the same atomic number, so protons never change in any of these, ever. But isotopes have a different number of neutrons, okay? So keep these like separate in your mind. Okay, this might be a better angle, I don't really know. Okay, so the next question says that Democritus said that blank were indivisible, fundamental units of matter. So remember, this is the first guy I told you about. This is where we first had the idea of an atom, okay? So this guy is associated with that first idea of an atom. And remember, we talked in class as to why, as to why he didn't have like experimental proof that these things existed, and it was a very long time ago. I believe we Googled it, and it was, I believe, 80 years after the Acropolis was built, and he was a Greek, and that was pretty interesting, at least to me, maybe not to you, but that was really cool. I've never thought about it because I've always taught this in America and didn't think really about when the Acropolis was built and when the atom and Greeks, and so I thought that was really neat. All right, so M, an anion is an atom with an overall blank charge. Remember, anions are negative, okay? So an anion is an atom with an overall negative charge. And I don't have it on here, but I'm going to go ahead and tell you that, remember, cations has an overall positive charge, okay? Just kind of for reference. All right, so an atom gets an overall positive charge by, remember, all of these charges are either increased or decreased by electrons. So if it's going to be a positive charge, they're going to lose an electron, okay? So they get that charge by losing electrons. Okay, If they have an overall negative charge, they would get it by gaining electrons. So just keeping that in mind. Okay, so next it says to explain the 4 major points of Dalton's atomic theory. It's on a slide in our PowerPoint, so I'm not going to write all of it down. You guys wrote it in your notes, so I'm not going to write these down, but just on your notes, there is an actual slide that tells you Dalton's atomic theory, and I would just write those there. So I'm going to actually skip this part. Also, the next one is also exactly from your notes, but it says explain in detail Rutherford's gold foil experiment. Explain what was going on when particles were deflected at small angles and at large ones. It may help to draw a picture once you write your explanation. So this is a pretty big deal on the test. So basically, remember Rutherford's gold foil experiment. He had this like shield that let me draw it. That would actually show where the alpha particles landed. So he's shooting these alpha particles, and in class we talked about how he shot them. It was actually, I actually didn't know at first, but you had the question, so we researched it. But he would shoot these little alpha particles, which are positively charged particles, on a piece of gold foil. Gold foil. And we'll go ahead and say that that's an alpha particle. Okay, so he would shoot these through, and he used radium. Remember, we talked about it again. We used radium and to create the alpha particles. And so he shot it through, and he said if, remember J.J. Thomson had that plum pudding model, and it was like just like a ball of positive charge with little electrons dotted in the middle of it. So he said, if this is true, then it should just the alpha particles should just kind of go through without interruption, is what he said. So he did this experiment, and he noticed that some alpha particles went straight through. Actually, most alpha particles went straight through just fine. Okay, and then he said he noticed. We learned that it wasn't actually him, it was his guys doing the experiment, but still. Then they noticed that some of these alpha particles were deflected, so they were going straight and then they kind of turned a little bit, okay? So straight and then they kind of turned a little bit, and so they were deflected at small angles. So since these are positive, we'll do conclusions afterwards. And then he noticed that some alpha particles actually bounced back, okay? He noticed that some of them were actually ricocheting off of something. So his conclusions for that, he said, since most alpha particles went through completely, he's going to say that he concluded that most of the atom, sorry, I hit my glasses on the camera. Most of the atom is empty space. Okay, I'm thinking and writing, that's bad. Okay, most of the atom is empty space. So basically, because all these alpha particles went through, that most of the atom is empty space. And then he said there is something positively charged. There's something positively charged in here, and he said that because some of these were deflected, okay? So they were pushed away from it. And since this alpha particles are a positive charged particle, that they were deflected. So he said it's positively charged and only a few of them bounced back, okay? So a few of them bounced back, and so the fact that they could bounce back, they were dense. He said they were dense, okay? So can you guys see? Yeah. Okay. So basically, this gold foil experiment, he just shot a bunch of alpha particles. Most went through, so he said most of the atom's empty space. Some were kind of curved, so there was and since this is positively charged, and positive will repel a positive charge, he said that it was a positively charged thing inside. He didn't know what it was yet. And then he said, because some things were actually deflected in alpha particles, if I remember, I think it's like 2 protons and 2 neutrons. So it's a little positively charged, like tiny nucleus thing. And it was thick, it was dense enough to ricochet it back completely. So he concluded that it was dense. So let me make sure I answered all the questions. Explain what was going on when the particles were deflected at small angles. So we did. That's kind of like that. And then it says it may help to draw a picture. Okay, so yeah. So basically, this is what was expected, the hypothesis. If J.J. Thomson's model was correct, he said it actually didn't do that. It did a lot of these little things. So there's something tiny, dense, and positively charged, and then the rest of the atom is empty space. So that was the conclusion that he came up with this gold foil experiment. Him and his group were kind of a big deal after that. They changed the game. It wasn't this. Now we have this like little nucleus, and then a little nucleus with like little electrons going through type thing. Okay, you probably have seen that model, and it's like this little planetary model, which is totally incorrect, but it changed from this model to that model. Okay, next, number 4, how did Thomson know the charge of the particle he discovered was negative? So remember, this is the guy that discovered the electron, and he said, there's something in here that I've discovered, it's negative. So he discovered it's negative because remember that cathode ray tube, and there was a positive plate and a negative plate, and everything was attracted to the positive plate. So basically, he said that the electron was negative because it was attracted to the positive plate. So I guess the answer I would write is the particles in the gas the positive plate tube. Okay, so that's how I would write it. So just make sure you know that Thomson's experiment, he discovered the electron, and he discovered it by putting an inert gas in a cathode ray tube, and then it was attracted to the positive plate in the tube. Okay, next. So this is the last thing that we've learned. This is where we're actually finding out how to calculate atomic mass. So remember, guys, the atomic mass is this. Let's see if you can see it. Is this. So this isn't what every single magnesium atom weighs, okay? So remember, keep in mind that this number is a combination of all isotopes. Oh my gosh. Keep in mind it is a combination of all isotopes and their weighted average. Okay, so again, not all magnesiums weigh, no magnesiums weigh exactly that. Keep in mind that this is magnesium and all of its other isotopes averaged to its appropriate weighted average. So most of magnesium ions, if you'll notice all of these elements that have isotopes, I said ions, oh my goodness, most of these elements, most of these elements and their isotopes, they have a huge amount of one isotope and then like very tiny other isotopes. So like, for example, magnesium, you're not going to see like 25% has, so this is 12 protons, so 25% have 10 neutrons, 25% has 11 neutrons, 25% has 12 neutrons. You're not going to find like evenly distributed isotopes. It's going to be like, usually it's like 95% or more are one single type, one single isotope, and then you have like very small amounts of other isotopes. And that varies, like it's not just like all even around the world. We calculate that by collecting a sample of magnesium, and that could change depending on where we collect that sample. It could change on when we collect it in time. It could change on where we collect it in the universe. So keep that in mind, that this is just a weighted average of isotopes, and that usually there's one big chunk of 1% of the same isotope, and then there's little ones. So yeah, anyways, I'm talking too much, sorry. So the question says, an element has two common isotopes. The first isotope, can you see? The first isotope has a mass of this and occurs this much of the time. The second isotope has a mass of this and occurs this much of the time. Calculate the atomic mass of this element. Remember, guys, this is just like calculating your class average. So we have like a grade, so like a test grade, and then remember this percentage of the time that you find that test grade. So that percentage is like how much that test would be worth, okay? So if you get a really bad grade on a test, they're worth so much more, so it's going to bring your grade down more, okay? And if you get a really good grade on your homework, remember homework's worth only 5%, and if it's only 5%, it's not going to change your grade very much. So this is all we're doing, is just calculating the atomic mass given a mass and a percentage. So all you have to do in this case, so the atomic mass, I don't know, we can do AM if you want, however, whatever you want to abbreviate it by. So the atomic mass is equal to the mass times the percent, but in decimal form. So I know that looks like it's decimal form, but we're going to take this percentage off. So either you can take 60.10 divided by 100 to get it in its numerical form, or you can just move the decimal over to the left 2 times. So to calculate atomic mass of this, whatever this element is, you do 68.926 times, you can either do 60.10 divided by 100, okay, that should be one big thing, okay, or you could just, when you calculate that, it's just basically moving the decimal over to the left by 2. I guess I'll go ahead and do it now just to show you, but I'm not going to do it every time because we do have lives and we don't want to watch this all the time. So basically, can you see this? Let me see. Yeah. Okay, so basically we're going to take, what was the percentage? 60.10. So 60.10, and you would divide it by 100, and so all that's going, okay, all that's going to do is move the decimal over, okay? So if you're on the test and you don't want to do the whole divided by 100 thing, I usually will just skip to 0.601 or 0.6010. Okay, moving on. We're going to take the second atomic mass, 70.925 AMU. Oh, I didn't put the units there. Oh well. And I'm going to do it just moving the decimal over. So 1, 2, so that'll be 0.3990, 0.3990. Okay? And then just calculate it. So I'm just going to type it in the calculator. I can't see. 68.926 times 0.601. I just put equals, so 41.425. Okay, so 4245. We're going to keep the significant figures. Okay, all right, now we're going to do the second side. I like to do these, you do it however you want. I like to separate and do the calculation a certain way. So this is how I do it. 70.925 times 0.03990. So that's what I get. I'm going to write with the correct significant figures. I'm going to put 20. It didn't look right. I noticed I put the 0. I'm sure you're like screaming at me on the computer screen. 25 times 0.3990. Okay, much better. All right, so that is 0.3, and we're going to keep that significant figure, you know, that's going to round. All right, thank you for yelling at me at your computer screens. I kind of heard it apparently. All right, so now we're going to add, and remember with the significant figures, we're going to have 2 digits past the decimal. Since both of them have it, we don't even have to decide. So we're going to add 41.42 plus 28.30. And our answer is going to be 69.72. And keep in mind that that's atomic mass, so it's 69.72 AMUs. Okay, so that's the 2 common isotopes. If for fun, let's look at what might be 69.72. That might be gallium. Okay, just right here. Might be gallium. Okay, moving on. Let's do another one. So nitrogen has an atomic mass of 14.007 AMUs. Nitrogen has 2 common isotopes. One of the isotope has a mass of this much and a relative abundance of this percent. So it wants us to know what the percent abundance of the other isotope is and what the mass of the other isotope is. So we know, so remember here's our calculation. The atomic mass equaled 1, I'm sorry they're doing construction if it's too loud, but I'm pretty sure I'm loud enough. The atomic mass is equal to the mass of each isotope times its percent abundance, plus the mass of the other isotope times its percent abundance. Here we're going to do the same thing, except now we have that initial atomic mass. And then this is the mass of another isotope, okay? So we have... here we have our answer. So 14.007 is our atomic mass of nitrogen. That's what's on the periodic table. Right here. Okay. Sorry, the guy asking for our scraps is going across. Now, we're going to do the mass and abundance percentage of the first isotope, and we don't know the others. So we're going to write what it gives us, 14.003 times the percent abundance, which I'm just going to move the decimal over 2. I'm not going to do the division. So 0.99632. We're going to keep those significant digits. Plus, we don't know the mass of the other isotope. It's asking us here. So we're going to call that X, okay? But we can decide what the percentage is, okay? So all you have to do that is just do 100. I am doing this in my own way. That's going to frustrate me in a minute. Minus 99.632. Most of you can do this in your head, but if I did, I would just mess up because I'm talking and I am writing and I am thinking. 99.632. So the answer... okay, would be 0.368%. So the answer is 0.368%. I think my first block I made the mistake of not changing it. So remember, this is the percentage. We still need to convert this into its numerical value. So we have to do 2 decimals over, okay? So we need to move it 2 decimals over to keep that... to turn it into its numerical value, so 0.00368. I'm going to keep the significant figures. These are not significant. These are. We had 3. Okay, so moving on, we just do some algebra, okay? So with algebra, this, guys, you can do whatever you want. You can multiply this and then subtract it and put it on this side. Remember, we talked about it in class. That's really up to you guys what's easiest. I'm going to go ahead and multiply it just to get rid of some of these numbers since I'm writing in my own space. So we're going to do 14.003 times 0.99632, and that's going to equal 13.95. How many significant figures? I have 1, 2, 3, 4, 5. So I have 5 significant figures. So let's do 1, 2, 3, 4, 5. It's not going to round. So we'll do 5, 1. Okay? Plus, we're just going to bring this down, x 0.00368. Okay? Now we're just going to, what I would do is, I would subtract. Let's finish this equation before I mess it up. I'm probably not the best math teacher. I'm going to do this, get that out of my vision. All right, so I'm going to, since this is added with this, in algebra, you would just subtract it. I'm not really going to teach the rules of algebra. You should have come to me knowing that. Okay, so then the equation is now, I'm going to go ahead and actually do that so I don't have to write multiple numbers. So 14.007 minus 13.951 equals 0.056. So 0.056 equals x times 0.00368. Okay, so now to get x by itself, all we have to do is divide everything by 0.00368. Okay, so then, oh my gosh, I'm so sorry, y'all couldn't see that. So now, I'm so sorry, I'm not going back. So now we're going to do x equals, I'm going to go ahead and calculate what that divided by that is. I am super sorry, y'all couldn't see that. Can you see that? Okay, you can see now. Okay. All right, so we're going to do 0.568, nope, 0.056 divided by 0.00368 equals, okay, so it equals 15.21739113 is what my calculator says, but that's not okay because we need to take into consideration significant figures. So if we'll look up here, we have 2 significant figures here, 3, so we're going to just kind of take it down to 2. So we're going to stop here, we're going to look at this, it does not round that one up, so x equals 15. Okay, simple. Sorry, AMUs. Okay, that's it. Quick maths. So the answer here, 0.00368. Can you even see? Okay, the answer here is 15 AMUs. That's it. Okay, last page. So on the test, obviously there's going to be a chart. There was one on your quiz. So make sure you look and see if you got the concept or not. On the homework, some of you were getting kind of stuck on trying to figure out a charge. So if I don't give you a charge and I don't give you a different, remember charges are created because you have a certain amount of protons, and if the electrons don't match the protons, there's a charge. So if there's more electrons than protons, it's negative. If there's less electrons than protons, it's going to be positive. So if I don't give you a proton or proton or electron number, and I don't give you a charge, it's unfair of me to ask you to tell me the charge. So just assume that that's neutral, okay? So we're looking at this. So remember, just a quick review. This is the mass number, okay? So that's the mass number. And then the bottom number is the atomic number. So from these two numbers, we can actually fill in all of these squares, okay? The atomic number, obviously, we can fill it in right here. So it's 14, right? That's literally what that number represents. But if you didn't know that, that'd be difficult to do. So the mass number, if you look, that's, again, that number. But again, if you didn't know that, it would be also difficult to pick one. Number of protons. Remember, the number of protons always equals the number, the atomic number. Okay? So that's also going to be easy. So, for example, if you have these two columns and they're not identical, we've done something wrong because the atomic number is, we literally get that from the number of protons. The number of neutrons, you're going to have to do a little bit of math. You're basically going to subtract 29 minus 14. So you're going to subtract the number of protons from the mass number, and that's the number of neutrons. Because remember, the mass number is basically this plus this equals this. So if you flip that equation around, this minus this equals this. So the number of neutrons is going to equal 15. 29 minus 14 is 15. And then the number of electrons, since we're assuming it's neutral, we're going to say it's the same as the protons. Okay? We assumed it's neutral because we did not have a charge right here. We didn't. So we're going to assume it's the same. Okay? Alright, so now we don't have a symbol, but we have an atomic number, and we have a mass number, and we have number of electrons. So let's look and see, where's my periodic table? Here it is. Okay, so let's look. So it's the atomic number 23. So I'm going to go to atomic number 23, which is vanadium. Okay, so we're looking at this, and then vanadium's mass number is 51. So we're just going to put the symbol here. We're going to start filling this out. So vanadium, so that symbol is V. Okay. The atomic number will go down here, so V23. And then the mass number will go up here, 51. So easy. Okay. And then number of protons always equals the atomic number, so we know that's 23. Okay. And then the number of neutrons is basically this minus this, and that will give you your number of neutrons. So 51 minus 23 is going to be 28. Okay? And then number of electrons is 23. So now it looks like we're done, but actually we're missing this guy right here. I know that we're missing a charge because I see that the number of protons, oh, I lied. There's the number of protons and the number of electrons actually match, so we're good. I'll be quiet. Move on. Alright, now we're missing symbol, we're missing atomic number, we're missing mass number, but we have number of protons, neutrons, and electrons. Again, I'm going to go ahead and just check this. They're the same, so we're not dealing with a charge here. We're not dealing with an ion. So we're going to look at number of protons. Remember, the number of protons equals the atomic number. So let's look and see what we're dealing with. Atomic number of 77. So I'm going to look on my handy dandy periodic table. 77, so that is this one. Okay, iridium. So we're dealing with IR is our symbol. IR, okay. And then we know that the atomic number is equal to the number of protons, so 77, 77, and then the atomic number also goes down here. Okay, the mass number, that's something we don't have. We don't even need to use the periodic table for this. What we're going to do is we're going to take this plus this, and that's going to equal, that's actually a plus sign, that's dangerous that you guys might think it's a minus. Plus sign, and that's what that the mass number is going to equal. So iridium's mass number is 192 if you were to add these two together. So then the mass number will go up here, 192. And then just one more time, because I always make mistakes, I'm going to check to make sure protons and electrons match, so we don't need a charge. Okay, moving on. We have indium, I think. So indium, and we have its atomic number and its mass number. So I'm going to go ahead and fill those in. 49, 115. And then the protons, again, it matches, so 49. We just need to figure out the number of neutrons and the number of electrons. So this is where it gets tricky because now we have a charge. So this is new to this review. So we have 49. So how to determine number of neutrons? You take 115, you subtract 49. We already know that. So we're going to say that there are 66 neutrons. And then the number of electrons. So technically, I'm going to go ahead and write it in this little box, but just kind of stay with me because the answer isn't the first thing I write. So technically, if it was neutral, we would have 49 electrons, right? But it has a positive charge. It has a positive charge. So if it has a positive charge and it represents electrons, which are negative, we're actually going to take away 3 electrons from the neutral atom. So if it's a positive 3 charge, that means we've lost 3 electrons. So we're going to take 49 minus 3, so then our actual answer is 46. That's how we determine the number of electrons based on an atom or a symbol that has a charge. Moving on. Okay. All right. So we have no symbol, no atomic number, but we have a mass number and we have number of protons. And we have number of electrons. So whatever's happening has a charge because these two don't match. We have a number of protons, so we have an atomic number. And if we have an atomic number, we can look on our periodic table and find its symbol, which was, what was it, 47? Silver, okay? Silver, which is Ag is the symbol. So Ag, okay. Our atomic number will go on the bottom. Our mass number will go on the top. And then we need to put a charge because these two don't match. But first I'm going to go ahead and do the neutron calculation. So we basically take 108 minus 47, and that would be the number of neutrons, which is 61. Let me just make sure. I'm second guessing myself, sorry. Yeah, okay. I didn't like this. Okay, moving on. Okay, so now we're good, right? No, you're yelling at me on the screen because I haven't done this guy, right? All right, so we're gonna look at this. So we have 47 protons and we have 46 electrons. So we have 47 positive charges and 46 negative. So we have one more positive charge than we do negative. So it's a +1 charge. Okay. Moving on, we have atomic number 51. So let's go ahead and just look at atomic number 51 and see what we've got, which is, I don't know, can you see this? No, yeah, maybe all the way at the edge, but anyways, atomic number 51 is antimony, okay? Atomic number 51 is antimony, which is Sb, okay? We have our atomic number, so we can go ahead and write that. We don't have an atomic, the mass number yet, but if we have the atomic number, we know that the number of protons will equal the same. We have neutrons, so we can actually add these two together to get the answer. So if we have 61 plus 51, that's going to equal 112. So our mass number, we're going to go ahead and put it here, 112. And let's see, the number of protons do not match number of electrons, so we're going to have an overall charge. We have actually 3 more electrons than we do protons. So we have 3 more negative charges than we do positive charges. So we're going to have a negative 3 charge. Okay, moving on. Cobalt. Cobalt. So cobalt is mass number 59. We have electrons, and that's basically all we have to go on. It would be difficult to do that without a periodic table. So you would look for cobalt. I'm going to find cobalt. I happen to know where it's at because I've done this for a while. Cobalt is here. And the atomic number is 27. So we're going to go ahead and write the atomic number is 27. So that means this 27 goes at the atomic number at the bottom. 59 goes at the top. Okay, number of protons equals the atomic number, 27, and number of neutrons just equals 59 minus 27, which is 32. Now, protons do not equal electrons. So in this case, we have 27, 24, 25, 26, 27. We have 3 more positive charges than we do negative charges. So it's a +3 charge. Taxi. Oxygen. Okay. So, this one is a tricky one because it gives us the symbol and it gives us neutrons, and that's it. So, oxygen is right, I don't know if you can, okay. Oxygen is right here, its atomic number is 8, okay? So we have oxygen here, its atomic number is 8. That means its number of protons is 8. Number of electrons, it doesn't indicate a charge, so we're going to assume those are 8 as well. The mass number, you're just going to do 8 plus 8, which is 16. So then you have 8, and then up here 16. There's no charge because it didn't indicate a charge, and so we're just going to assume no charge. So keep that in mind if you're on the test and you aren't given a charge and you don't know if the electrons and protons were different because it was a blank. Remember, all we had was the oxygen and the 8 for the number of neutrons, so we didn't know. So we're just going to assume neutral. All right, bromine is the last one. We have all of our information here, so we can basically fill it all out pretty easily. Atomic number, 35. Mass number, 80. From here. The number of protons is basically, not basically, it is the atomic number. Number of neutrons, you're just going to take 80 minus 35, which is going to be 45. And then there is a -1 charge. So you have one more electron than protons. So you would write 36. Okay? So that's it. Any questions, you're welcome to email me. Your test, I'm going to say, is going to be on like the first time you see me next week. I'm going to put it in Moodle. It was supposed to be this week. However, I'm losing a few classes due to the map test. What else? Your model is going to be due the second time I see you this week. Monday we should be having a lab, and Friday we'll do some type of review. Okay? So also I wanted to tell you guys that we will be doing lectures on Moodle as homework. And you will be responsible for doing your homework as well. But I will be giving you like the answers to make sure that you can check it on your own, and then you bring questions to class. And that way we can have more time for labs, because the labs tend to be the things that gets pushed away or will get dissolved in these classes that I lose for like map tests and some of the things that just aren't on the schedule at the beginning of the year when I was planning. So, and you guys are taken away from me. So we're going to go ahead and do that. On Moodle, you guys voted. There were more yeses than nos. So either way, I think we're good there. And I'm going to place the answers of the homework on your on this video right after this. So good luck studying. The review is worth 5 points extra credit, and it will be every test all year, so don't be surprised. You're not if you've watched this whole video. Okay, bye.